So the quietness of this class, I don't know if you guys are getting it or not, or if you're just thinking I'm going to get it later. And I know that that's how some of you guys roll. Tomorrow, workday, and then Friday we have the common ion effect. So if you understand this equilibrium stuff pretty decently, we might be able to talk experiment this while that's hopefully printing. But basically imagine if you had sodium chloride dissolved in 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 water. Right? So we understand that it has a certain solubility product constant. So there's a certain amount of sodium chloride. We could get the molarity of that. What happens when we put sodium chloride into water? What is the dissolving process? What happens with that? Dissociation, sodium and chloride ions, right? And we know by looking at that that solubility product constant, a certain amount, it may be all of it, or maybe mostly dissolved. But imagine we already have those Cl particles in there, and then we add some calcium chloride. So that's going to affect the actual chloride ions that are dissolved in that water already, is going to affect how much of the calcium chloride can dissolve. Because instead of starting with 0 with our solubility product ice table, we would already start with a certain concentration of the Cl. So that's basically what the common ion effect is. So basically it's the same thing. Instead of starting with 0 for something, you end up having to start with something. Let me go see if those are printed. I'll be right back. One of them printed. One of them printed, but I think we're just going to have to do it by screenshot. Boom, 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 boom. What's the best way to do this? It's like there is a force working against me today. Do you? No? You promise. All right, can you see the whole screen down here now? Thumbs up or give me a yes if you can.
Yes.
Thank you. All right, so if you're not watching these videos, I did not have time to make one of these, like a worksheet up on this, but we are going to discuss this. If we're looking at equilibrium through diagrams, and this is the way, there's a few ways that these questions can look. So if we're looking at this, we assume, if we're not given the volume of this container, we assume it's 1 liter. So looking at that, let's get the concentration for Q at equilibrium, Y at equilibrium, and then Z at equilibrium. I need a pen. So at equilibrium, case would be Q, and I want to bring this over here and put this right here. Case would be Q is Z over Q and Y squared. Hopefully that's not too small at home. So how many Q's do we have? 1, 2, 3. So that is 3 moles per liter. And we can just do 3 particles, you know, it doesn't matter. How many Y's? 1. And how many Z's?
12.
12. At equilibrium, do we expect this to be well above 1 or less than 1? If Z is our product? Above, right? So then if we take a look, we have 12, 3, and 1 square, which is 1. 12 divided by 3 is 4. This case of BQ is equal to 4, which is above 1. Makes sense. Products are being favored. So now we are going to look at reaction vessel A, and we are going to determine what we call Q. Remember, Q is the quotient. That doesn't necessarily mean it's at equilibrium. So if we count these up, we've got 3Q, 2Y, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we'll just call this Q1. 14, 3, and 2. All right? 14 divided by 3 divided by 4.
It's about 1.1666.
So we get 1.16 or 1.17 for the Q for reaction vessel A. Where is this system going? What is it favoring? The forward reaction will be faster or the reverse reaction will be faster? We're at 1.17 for this reaction vessel, and we need to be at 4.
So it would be the forward reaction because it needs more product.
Got it. We need more product, so the forward reaction is going to be faster. Let's do Q2 for reaction. Actually, I'll just call it Q sub B. So we have, anybody count the blues on that one? 2, 4, 6, 8, 10, 12, 14, 16. And 1, 2, 3, 4 for the Q. And a 1 for the Y. So what's that going to be? 16 divided by 4, 4. What's going to be happening with the system there?
It's equilibrium.
The equilibrium. So the system, we're still going to have, you know, Q's and Y's becoming Z's, but we're also going to have Z's becoming Q's and Y's. That's that dynamic equilibrium. The ratio of each of them is not going to change. Yeah,
Mr.
yeah.
Jackson.
Yeah.
So does the ratio of like the products to each other have to stay the same? Because like in the first one it's 3-1, but in the second, or in I guess in this one it's 4-1. Is that, or yeah, 4-1? Is that a problem? Like,
No,
does it have to?
it's because it's the overall combination.
So there can be like
In the
different
reaction
ratios.
down here it's 4-1, and here it's 3-1.
Yeah, like is
Yeah,
is
the
because
fact that we have less, of this than we do have here, yeah, it's not going to be a
So-
factor. It's just
so there doesn't need to be any consistent ratio. Okay.
nope. And the last one. Oh, I can't find my cursor. There we go. Reaction vessel C. The Q of C equals 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 to 1, 2. 2 squared, which is 4. So that's going to be 5. That means we're favoring the reverse reaction. The reverse reaction is going to be faster. One thing they don't want you to write, and I haven't talked much about it, is they don't want you to talk about shifting left and shifting right. So I've never been a fan of that. I don't know if Ms. Cotton used it, but you should probably try to get that out of your writing vocabulary. The best way is to say that the forward reaction will be faster, or reverse reaction will be faster than the forward reaction, because that clearly lets you know that you understand that versus using these fancy words. Questions there? Maybe this was better than printing it out anyway. Maybe this force that's been against me all morning is actually working for me. At what time does the system reach equilibrium? Justify your answer. What would you be looking for here? They give you the information at 0 minutes, 10 minutes, and 20 minutes, and then 30 minutes.
You'd be looking for a consistent ratio.
Exactly. So you would make products over reactants or whatnot, or basically you don't even have a formula. You don't need it. You basically are looking for a consistent ratio on this. So by adding those up, you can make a table. And where do we have a consistent ratio starting and forming this
20
one?
minutes.
That you might be able to see it. 20
20
minutes.
minutes.
Yeah, right. At 20 minutes, we can see that we get to the point where we have a consistent ratio. This diagram is a little bit different because they actually tell us, and I love the, oh, that's awesome. Give us a sign. Hey, we're having some awesomeness happening here. Let's try this. No? Maybe we're back to good. All right, so if we take a look here, this is another one of those things that's silly, but reading through there, what makes this different from the first problem we did? So each particle here represents 0.020 moles. What else did they do that's really tricky? And this kind of stuff is kind of garbage in my opinion, but
They made it 2 liters.
they made it 2 liters, which means that we don't just have the 1 liters, so we take the 0.02 or however many we get from that and divide it by 2 in order to get the actual molarity. So they say determine the molarity of Q2, Z2, and QZ. Luckily, if they're asking you for that, then that might be an idea for you to sit there and say, okay, that means there must be some little trick to this at least. So if we take a look, well, they didn't identify Q. Oh, look, I thought they were, yeah, I'm glad they put that there. I thought they were just going with the written word 2 liter. So that's good. So if we take a look, they did not identify what was Q or Z. They did identify, well, we don't have to identify what QZ is though, right? Let's do Q, Z, and QZ. So we can make the reds or the blues Q or Z because each of them have the same what? Number right? And there are 4 particles. So 4 particles. Every 1 particle. Actually, let's go ahead and just do this like this. There are 4 particles per the 2 liters. Every 1 particle represents 0.020 moles. Particles will cancel out. We will get moles per liter. 4 divided by 2 is 2. 2 times 0.02 is 0.04 moles per liter. And how many QZs are there? 3. So we have 3 particles per 2 liters. Every 0.02, every 1 particle is 0.020 moles. What do we get there? 6.06 divided by 2 would be 0.03. Right? What are we expecting our equilibrium constant to be just in our head at this point? 1, greater than 1, or less than 1?
Less than 1.
Right? If we're seeing more product, I'm sorry, if we're seeing more reactant, and we're assuming that this will be less than 1, let's go ahead and set up our case of BQ. Because this diagram is at equilibrium. So we have 0.030 squared, and we have 0.040 times 0.040. So that also would be squared. 0.03 squared divided by 0.04. We get 0.5625, which makes sense. It is less than 1. Questions about equilibrium problems using particle diagrams? No, no, no. All right. Cool. Using diagrams, sample problems using ice tables. Dun, 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 dun. All right. So let's take a look. We did some of these yesterday. And we actually used the solver function, right? So one other thing that you can do instead of using the solver function or the quadratic equation, a lot of times these numbers are so small that they're not going to have an effect on the actual bigger numbers. So if we take a look, x here was 0.0136. In reality, if we take 2 minus that 2 times the 0.0136, it's probably not going to affect the significant digits on this, because I think even the significant digits on this would probably be still, instead of 1.9, it would be 2.0. So 2.0 minus 2 times 0.0136,
It's 1.9728.
still 1.9728, right? Which would then round again to 2.0. So what you can do is if you have something like this, you can actually ignore the minus 2x here and just put 2 squared there. And if it's multiplication, you can ignore it. But if it's addition, subtraction, you can just ignore it because it's so infinitesimal that it's not going to matter. Well, what does that mean? Well, then we should have something that we can factor more easily to solve for the x. All right. Let's do one and calculate the concentration of each species initially. 1 mole of each substance is placed into 1 liter flask. That's awesome. All right, so let's do a rice table. So for equilibrium, K sub EQ for the following reaction is 510 at 700 Kelvin. Calculate the concentration of each species if initially 1 mole of each substance is put into a 1 liter flask. So initially we have 1 mole of this, 1 mole of that, 1 mole of this, and 1 mole of that. Well, that's moles per liter, so that will act as a similarity. So what they're really asking us for this one is, do we know which way the system will go? Which reaction will be favored, forward or reverse? Currently, we have an equal number of moles on both sides, but we have a K sub EQ, so we should have an idea of what we should have instead of 2 moles for 2 moles. We should have more what at equilibrium for this?
You should have more product.
We should have more product because the K sub EQ is 5.10. That's greater than 1. We should have more product. So which reaction is going to be favored? Forward reaction will be favored. That means that we will lose minus x, and we will gain plus x and plus x. Right? And then on here, we have 1.0 minus x, 1.0 minus x, 1.0 plus x, 1.0 plus x. So K sub EQ equals that 5.1. And it looks like what we're going to end up with is products over reactants as always, 1.0 plus x squared over 1.0 minus x squared. Is this one of those that we could sit there and say that we ignore x? If we ignore x, do we have anything to solve? No, unfortunately not. So we would have to do something here. What would you guys normally do? Would you just go ahead and square root both sides mathematically? Or would you just use a solver for that? What's that? Square root of both sides? All right. You don't like typing all that junk into the solver? So we get 5.10 square root of that equals 1 plus x over 1 minus x. Would you do the solver math? No. So let's go ahead. What is the square root of 5.1? And if you guys have some mathematical way that's better than this, by all means, tell me. So I'm going to go ahead and take the square root of that. I get 2.258. And I'm going to go ahead and multiply this. 2.25, actually this 2.26 minus 2.26x equals 1 plus x. So then I will add 2.26x to both sides, which will give me 3.36 or 3.26x. And then I will subtract 1 from both sides, which will give me 1.26. Then we will take 1.26 divided by 3.26. And we get 0.387 or 0.39. So we will take 1 minus 0.39. So that will give us 0.61 for each of these. And what did I say, 0.39? 1.39 for each of these. Do we have more product than reactant at equilibrium? Yeah. Questions there? So quiet. What's the matter, Gabe? Nothing. All right. A lot of work for a little answer at the end. Is it depressing or no? All right. What do you think? Fine. It's fine. Yeah. All right then. I'm going to suggest you guys do problems 1 through 8 for tomorrow. The answers are on that link. I'll let you guys go. Unless you have questions, by all means, you can stick around. But that's it. That's all I got. Major thing today was doing the diagrams. This is way up, this is way below what math you guys are doing in your math class, I'm assuming. But so does it suck to have to go back, or is it just in there? No. All right. Cool. I just remember I don't enjoy these things as much as I do some of the other aspects of things too. So like I said, factoring and all that, that's not my forte. Well, I should stop the recording. Piper, are you okay? I'm gonna end this so I can put the, oh, she's gone.